Hello, welcome back and welcome to another video, a second video in our series on on the hydrolysis of esters. And the last video was base mediated and or base promoted, and I thought that had too few steps, so I decided I'd whip out the acid catalyzed version to sprinkle in a couple extra, well, 3 extra proton transfers. Now, back in the carboxylic acid chapter, we saw a reaction called the Fischer Esterification, where we took a carboxylic acid and an alcohol and turned it into an ester plus water. Well, this reaction is the opposite of that reaction. We're going to take an ester and we're going to hydrolyze it with water to make a carboxylic acid and an alcohol. Okay, and the mechanistic steps that we'll see in this reaction, this reaction is the microscopic reverse of the Fischer esterification. That means we have the same elementary mechanistic steps, but in the reverse order. Okay. All right, so let's look at an example of this. So what I want to hydrolyze, what do I want to hydrolyze today? Okay, I don't want to hydrolyze something too complicated because then I gotta draw a lot of stuff. Okay, so we'll hydrolyze this ester. Okay, and we're gonna do that under acid catalyzed conditions. So and everything's in equilibrium in this particular reaction. We're going to use water. It's acid catalyzed, so we're going to use an acid. I'll use paratoluene sulfonic acid. All right, and that's going to make a carboxylic acid plus ethanol. Okay. All right, so let's look at the mechanism of this reaction. And you'll note I said the base version of this was base promoted, whereas this is acid catalyzed. Okay, I consulted with my faithful assistant here, Professor Pink Penelope Pigtails, and she agreed with me that this was acid catalyzed, not acid promoted. So see, kind of looking at the mechanism, if you can figure out why that is. Okay, why would we call it an acid catalyzed instead of acid promoted? All right, and I'm going to have to go around the board a couple times on this mechanism because it does take several steps. All right, in an acid catalyzed nucleophilic acyl substitution, okay, I think you know what the first step is if it's acid catalyzed. Any comments? Okay, that's right, it's a proton transfer. Okay, so Alright, so we're going to transfer a proton. Okay, that gives us a stronger electrophile. Okay, and we want that because now we have a weak nucleophile that's going to come in the next step. Our weak nucleophile is water. Alright. And we're going to do a nucleophilic addition here. All right. And so that's going to add there. Alright, so far so good. I'm gonna momentarily screw up the mechanism. Okay. Alright, so that's after our nucleophilic addition. Alright. we're going to lose this proton to get to our halfway point. So we're going to have a proton transfer, nucleophilic addition, proton transfer. Basically making a proton transfer sandwich. Okay. And that gets us to our tetrahedral intermediate. Okay, now at this point it can be a little daunting. We've got 3 oxygens on this carbon, so you kind of have to, have to keep in mind this tie is too big for you, little pig. Yeah. Oops. Okay. You have to keep in mind where we're going. So we're going to lose this ethoxide eventually. So that affects our next step. All right. So let's do that. Okay. All right. So what do we got? Our proton source is para-toluene sulfonic acid. So we're going to protonate this, turn it into a better leaving group. Okay, so that's a proton transfer. Ooh. Ooh. Okay, PT. Like so. Ooh. Center that oxygen a little better there. Okay, we've got a little bit good leaving group, so it's going to leave. We're going to eliminate it. That's called a nucleophile. There's 2 electrons there. Okay, a nucleophile elimination. Whoa. Okay, that gets us to this protonated form of the carboxylic acid. And then lastly, to get to our product, we're going to have another proton transfer. Okay, and I'll use ethanol. Okay, we just kicked it off. Proton transfer. And that makes our carboxylic acid. Okay, and we, in this step, make a protonated ethanol. Okay. All right. So so in summary, what we've got here. I'm gonna erase this. Summary. Uh-oh. There you go. 2 M's. Alright. We've got a proton transfer followed by a nucleophilic addition, followed by a proton transfer, followed by another proton transfer, followed by a nucleophilic elimination, followed by another proton transfer. Now, the reason this is an acid catalyzed process, in some of these, other textbooks would call this a protonation. Okay, and then a deprotonation. Protonation, deprotonation. Okay. So from the perspective of the reactant or the substrate, or the reactant that we care about as an organic chemist, it's getting protonated. It's gaining a proton, whereas here it's losing a proton to a base. Okay, and what makes this an acid catalyzed process is that we've got a balance of this protonation and deprotonation steps. Okay, all right. So this is the acid catalyzed hydrolysis of esters, you can see it has a lot more steps than the base promoted process. That only had 3 steps. This has 6 steps, and that's really common that the acid catalyzed process will have more steps than the base process. All right, well, thanks for watching. That concludes our acid catalyzed hydrolysis of esters video. See you next time.